Hello friends, welcome to this lecture on computer-aided power system analysis. From this lecture onwards, we will be discussing the topic of fault analysis of power system. But before that, we have already said in the last lecture that we need to discuss the issue of measurements for power system state estimation. So, today we will first discuss that issue briefly, and then after that we would be actually start discussing the issue of fault analysis of power system. So, in the case of power system state estimation, so we are now talking about power system state estimation. So, power system state estimation, it will just take 5 to 10 minutes. After that we will start fault analysis. So, we know that the number of measurements M always has to be greater than number of states, and this is due to the fact that we need to take into account the presence of bad data, and in case there is any bad data detected, so then we need to remove it, and so then therefore our effective number of measurement gets reduced. So, to take into account that possibility, we need to ensure that always our number of measurements should be greater than the number of states to be estimated. Now, suppose for an example, that we do have let us say a 500 bus system, n is equal to 500. So, then in that case n would be 999. So, then obviously my m should be at least 100, at least 1000, in fact it should be much more than 1000. So, now the point is that if I have to put all these meters into the system, it may not be always possible, neither it may not be always very much feasible, neither it may not be always very much cost effective. So, then instead of using our physical measurements, we also use two other types of measurements. So, and basically these two types of measurements are called pseudo measurements and virtual measurement. Now, please note that these particular pseudo measurements and these virtual measurements are not the physically metered quantities. That means, we are not really putting any kind of physical meter to get these values, but we will get these values from some other information. Let us see. First, let us come to this aspect of virtual measurement, because it is easy to understand. Suppose that I do have a system like this: bus 1, bus 2, bus 3, bus 4, 1, 2, 3, 4, 1, 2, 3, 4, and let us say at all these buses except at bus 3 there are loads, and these loads can always change. So, then I really do not know that what these values are, but I know that there is no load at bus 3. So, then therefore, I can always say for surety that P 3 is equal to 0 and Q 3 is equal to 0 for surety, because there is no physical load. So, then therefore, these values of injected powers would be always equal to 0 come what may, right. So, then therefore, these information are very accurate information, right, and which are already known. So, then therefore, this kind of information which are already known very accurately, these are called virtual measurements. Virtual measurements means that we are as if that we are virtually measuring this without putting any physical meter there, because we already know what their value would be from the other sources, and these values would be quite accurate. Now, what happens in the case of pseudo measurements? Suppose for example, if we look at, let us say, a load at any bus, and these loads, all these loads at bus 1, 2 or 4, they can also vary. But now, if I know that their range of variation by some historical data, let us say that we do measure these loads for, let us say, for past 10 years, and then we have got all this data, and then we do something called, let us say, load forecasting technique. Suppose we do something called load forecasting technique, suppose we do employ something called load forecasting techniques, suppose called load forecasting, where, and this particular load forecasting module will simply give us the forecasted values of loads at bus 1, 2 and 4. Obviously, these forecasted values may or may not be equal to the actual load present, but then these values would be probably somewhat closer to the actual loads, right. So, then in that case, if I do use them, so then in that case I really do not have to put a meter for measuring these loads. Now, here in this case, here for example, in this case a total number of states to be measured is 7, that is equal to 2 into 4 minus 1. So, that is equal to 7. So, then therefore, I need at least 7 measurements. Now, if I have to put meters here, so then probably I need to let us say measure P1 2, Q1 2, let us say I also probably have to measure P2 3, Q2 3 and etc., etc. So, then therefore, I need to put at least 7 meters. But now, if I use these two virtual measurements, so then therefore, my physical number of meter needed is 7 minus 2 is equal to 5. So, then therefore, my actual requirement of the meters has got reduced. On top of that, if I perform say a load forecasting technique to forecast the loads at this particular bus. So, then I would be having the values of P4 and Q4, we would say that it is estimated, we should not say estimated, we should say that these are forecasted. Now, obviously, probably with all probability these forecasted values would not be exactly equal to these values had we put a meters at this particular location, but then with all probability these values would not be either too far away from these loads values. So, then therefore, if we also use these forecasted values, so in that case my requirement of total number of meters should be 7 minus 2 that is equal to 3. So, this is for virtual measurement and this is for pseudo measurement. So, you see, so then therefore, I am able to reduce my requirement of total number of physical meters by more than 50% if I use virtual measurement as well as the pseudo measurements. So, as a result, probably my installation cost and also installation cost of installing the meters as well as the installation cost of establishing the communication link from those meters to our central control center would be all reduced by half. Now, there is one small point to be understood. Now, we have already said that for any measured values we do use something called weights Wi, and we said that for any physical meter these weights are nothing but 1 by sigma I square, that we have already said, that is already equal to 1 by sigma I square. But what would be the weights for these meters as well as these meters, what would be the weights for these measurements, that is these measurements, and that is these pseudo measurements, that is these pseudo measurements which are nothing but the pseudo measurements, and what would be the weights for these virtual measurements. Now, these virtual measurements are already known values and which values are very accurately known, right. So, then therefore, we give these virtual measurements much more weight as compared to the weights we do give in even for these physical meters. So, then therefore, the weights of these virtual measurements we keep very high. On the other hand, for these pseudo measurements these values are not very accurate, but we hope that these values are also not too bad, but because these values are cannot be very accurate. So, then therefore, we do keep their weights to be relatively low as compared to the weights given to the measurements obtained by physical meters. So, then therefore, what is the final conclusion that so then therefore, what is the final conclusion that for power system state estimation we do use three different types of measurements. One is the physical measurement, which we call physical measurement, and then we use virtual measurement, and then we use also pseudo measurement, right. Their weights are very accurate, very high weights. Their weights are normal weights, and I mean this we already know, and their weights are low. And the total number of measurements M is nothing but total number of physical measurement plus total number of virtual measurement plus total number of pseudo measurement. So, then by using this philosophy, we do indeed reduce the requirement of our total number of measurements, or rather we do indeed reduce the required the number of required physical meters, thereby reducing the cost of the meters as well as the cost of the communication links. So, this closes the discussion on power system state estimation. Now, let us come back to our discussion of this particular topic, which we would be doing for the next couple of lectures, or rather the next lecture. So, what we start is actually fault analysis of power system. So, what we do is fault analysis of power system. Now, you may be wondering that when we are saying that fault analysis of power system, what we are trying to do. After all, in our standard course on power system analysis, we already do fault analysis of power system by utilizing sequence networks. We already do fault analysis of power system by utilizing sequence networks. Now, what do we do in the case of sequence networks? I mean, with this approach, this is already done. I mean, this is the traditional method. I should say that this is the traditional method. This is the traditional method, and this traditional method is utilization of sequence network. So, what we do in the case of this particular method, what we do, we simply find out for any for actually any given power system network, we do find out positive sequence network, we do find out positive sequence network, we do find out negative sequence network, and we also do find out the zero sequence network. We also do find out zero sequence networks. So, we first do find out the positive sequence, negative sequence, and zero sequence networks, and then depending upon the fault, then we interconnect these networks in a particular fashion. After that, what we do, we interconnect these networks, interconnect these networks depending upon the type of fault, depending upon the type of fault. For example, if it is LG network, if it is an LG network, then I know that this positive sequence, we call it positive sequence, we call it negative sequence, we call it zero sequence. We know that this positive sequence and negative sequence and zero sequence, this is negative, positive sequence, negative sequence and zero sequence, they are connected in series, that we know, this we have already learned, connected in series. Similarly, if it is for LL fault, then positive sequence and negative sequence they are connected in parallel, and if it is LL LLG fault, then these 3 sequence networks are also connected in parallel, something like this. Now this is basically the traditional method. Now this method works well, but there is only one simple problem of this method, is that for a large power system network we have to find out essentially 3 networks: positive sequence, negative sequence and 0 sequence. Usually this particular positive sequence as well as the negative sequence networks are essentially the same. So, then therefore, if we do find out the positive sequence network, then we also find out the negative sequence network, but finding out the 0 sequence network is little tricky, because this 0 sequence network depends on the transformer connection. As an example, if I have in a system, for example, if I have something like this, suppose something like this, that I do have a transformer and then something like this. So, then if both these transformers are star ground, so then essentially finding the 0 sequence network is very trivial. But then on the other hand, if these 2 transformers are, let us say, star grounded delta and let us say delta star ungrounded, so then therefore, for this same network, the 0 sequence network becomes completely different. And in any large power network, there will be at least hundreds of transformers, and these hundreds of transformers may have any connection. So, then therefore, for any given large power system network, finding the 0 sequence network is always a tricky issue. So, to avoid that, what we should develop is essentially a technique to analyze the behavior of a system upon occurrence of a fault in the phase domain. So, our goal is, so then therefore, we should have essentially we should analyze the fault behavior of a power network, analyze the fault behavior of a power network in the phase domain, that is not in the sequence domain, So, this is our goal. So, in this course or in this lecture as well as the ensuing lectures, we would be trying to find out, or rather we would be actually discussing the method of analyzing the fault behavior of a system not in the sequence domain, but in the phase domain, such that we do not have to find out 3 different networks of any given power network, but not 3, let us say 2. So, at least if I am able to develop this technique, so then in that case our advantage would be that we do not have to find out the positive sequence network as well as the 0 sequence network of any system. So, then our work would be much less and it would be much more convenient. So, essentially the goal of this module of this lecture is to discuss about the techniques of analyzing the fault behavior of a power network in the phase domain, but not in the sequence domain. So, then therefore, we will not be talking about development of the sequence networks, but rather we would be talking about how to analyze the effect of a fault in the phase domain. Now, when we talk about phase domain means, that means we are talking about in the ABC phase domain. So, essentially we are talking about ABC phase domain. And please note, because our faults can be asymmetrical, that is, we can have faults LG, LL, LG. So, then these are nothing but the asymmetrical faults. Because our faults can be asymmetrical, so then therefore, we now need to consider the power system as a 3-phase network, So, then therefore, whenever we are trying to discuss the fault behavior of a power system in the phase domain, and because we are going to analyze the fault behavior for all these types of asymmetrical as well as the symmetrical types of faults. So, then therefore, we now need to represent our power network in its totality, that as an unbalanced power network. That is, we should not assume that our network is a completely balanced network. Please do remember that so far, whenever we have discussed the techniques of load flow, contingency analysis, state estimation, etc., we have assumed that our system is a balanced network, because we have simply represented the system as an one line diagram. We have only represented the system only, let us say, as phase A or phase B or phase C, right. We have simply represented the system as a one line diagram, and we have essentially we have only represented only one phase of the system, assuming that this system is entirely balanced. So, then therefore, if we are able to calculate all the values corresponding to one phase, we would be able to calculate all the values at the other phases, because for a balanced system, the voltage magnitudes at all the phases would be equal and their angles would be just 120 degree phase shifted. But because here we are talking about asymmetrical fault, so then therefore, even if we have a totally balanced network, now suppose I do have a totally balanced network. For example, now we just take a very simple example. Let us say this is bus 1, this is phase A, this is phase B, this is phase C, and from this there is one line is going, then it is phase A, phase B, again phase C, and from there also another line is going, phase A, phase B, phase C, this is also phase A, phase B, phase C, this is also phase A, phase B, phase C, and let us say there are also loads connected here, there are also loads connected here, and there are also loads connected here. Now, here this is bus 1, this is bus 1, this is bus 2, this is bus 3, and these loads are all balanced. So, now let us assume that all these 3 lines are identical in nature, all these 3 lines are also identical in nature, and these loads are also equal to each other. So, then therefore, this entire network is completely balanced. But now, if there is a fault at this bus, just an ALG fault, so this is just an CG fault. So, the moment there is an asymmetrical fault, right, this operation of this system becomes totally unbalanced, because this same fault is not occurring here. So, then therefore, this entire system operation becomes unbalanced. So, then therefore, even if we have a perfectly balanced system, all generation is perfectly balanced, that is, all generated voltages are perfectly balanced, all lines are perfectly balanced lines, all loads are equal to each other in all the phases. But even then, if there is an asymmetrical fault, then the behavior of the system becomes totally unbalanced. So, then therefore, we have to first develop some technique for representing a unbalanced network through some proper appropriate matrix. Now, if we recall our discussion on load flow, we found or we have noted that for load flow analysis, in which we do consider our system to be perfectly balanced, and basically that is why we have represented the system as a one line diagram. We do capture this particular network topology and everything etcetera in the Y bus matrix. So, for representing a system, or rather for capturing the topology of the network etcetera, we do represent, we have utilized Y bus matrix, and this Y bus matrix is a very powerful matrix because it does capture the entire topology of the network in a matrix, and this matrix elements give us a lot of information. But this Y bus matrix we have only developed for a single phase system. Single phase system means that although our system was perfectly unbalanced, but then we have considered to be a single phase system, assuming that this system is absolutely balanced. So, then therefore, analogous to the case of a balanced system, here also we should first develop some method to find out the Y bus matrix of any given unbalanced network. So, our first task is to formation of, so our first task is to formation of Y bus matrix of a unbalanced network. Of course, when we are talking about unbalanced network, we are talking about unbalanced power system network. Suppose I do have, let us say, a 4 bus system. Suppose I do have a 4 bus system. So, now because we have to talk about unbalanced system, so now let us say I do have a 4 bus system, bus 1, bus 2, bus 3, bus 1, bus 2, bus 3, bus, and let us say I do have something like this, let us say 1, 2, 3. So, what I have is that these are the lines, these are the lines, these are the lines, these red lines are the lines, and these blue lines are the buses, and I have connection between and then we have so this is the case. So, what we have is let us again, so these are bus, and this is phase A, this is phase B, this is phase C, this is phase A, this is phase B, this is phase C, this is phase A, this is phase B, this is phase C, this is phase A, this is phase B, this is phase C. And let us say that this is bus 1, this is bus 2, this is bus 3, this is bus 4. So, we are considering only a very simple 4 bus system, and then we will try to understand that how to develop this Y bus matrix. Now, please note that here what we have done, we have simply represented the entire system by its 3 phase entirety. Now, at each phase of this system, now now essentially at each phase of all these buses there may be some load connected, or there may be some generator connected, or there may be nothing connected. So, then therefore, if there is some generator connected at this, at any of this bus in phase A, phase B and phase C. So, then therefore, these generators will give some injected current or some injected power. Similarly, if there is some load connected at some phase of some bus, so then therefore, these loads will actually draw current away. So, then therefore, according to our earlier discussion, in those buses also we can think of some injected current which are nothing but the negative of the load current. And on the other hand, if there is nothing connected at this particular bus, so then therefore, at those buses we can say that this injected current would be 0. So, then therefore, analogous to the case we have discussed for the single phase analysis, we can also have we can also have injected current II and P. What is IIP? It is the injected current at phase P of bus I. Now, here in this example I is 1, 2, 3, 4 and P is A, B, C, right. So, then therefore, I can have something like I3B. So, I3B means will simply denote that the injected current at phase B of bus 3. Similarly, I can also define VIP. Of course, these all are complex quantities. So, VIP, what is VIP? Voltage, of course, these are all complex voltage at phase P of bus I. So, in this case also I is 1, 2, 3, 4 and P is equal to ABC. Suppose for example, in the case of a balanced system, I would have simply I1, I2, I3, I4. So, then therefore, there would be only 4 injected currents, but now corresponding to each bus I have got 3 injected currents corresponding to 3 phases. So, then therefore, altogether I have got 4 into 3, that is 12 injected currents. So, then therefore, for any n bus unbalanced systems, the total number of injected current would be 3n, total number of injected current, and the total number of voltages would also be 3n, where n is the number of buses in the system, number of buses in the system. In this case, n is equal to 4, in this case n is equal to 4. So, with this short introduction we do stop. We will continue to discuss this important issue in the next lectures. Thank you.